Then we try to decouple the position and impedance control. We control we use the error-prone EMG to just control the impedance so that it will not spoil the accurate position tracking control. So basically, we work in the null space of the position control. And of course, this is true as far as there are no external forces, there are perturbations. So here is the very simple idea of what we do. We use a position reference, and we control through a classical PID controller, and we map to torques, and then we have the dynamics of the robot, and this is the control position, classical. And then we get from the EMGs, we take the whole EMGs, we project in the null space of that map, that Ozu-Gomi linear map, we project in that null space so that we take everything that is related to torques out of this signal, and what we get here has to be related to stiffness, right? Whatever is in the EMGs which is not torque has to be stiffness. And this we use as a feed-forward reference for stiffness. And then we implement this in the system. Okay, so we do these EMG measurements here, and we control the KUKA arm here. A very similar way to what we've seen in Patrick's lab. This is the system that we are using, OptiTrack and etc. We are using the real-time interface of KUKA. And here are the calibration for the EMGs. Now, calibration here is a Arash arm. And we have a few videos here. So, for instance, we can, let me show first this. Of course, I cannot go through all of them. So here is a rush arm. You see EMG's signals here and the position signal. You can see that the position reference is tracked with some error. When you stiffen the arm, the impedance of the arm is also increased, so the error is reduced. Right? Everything is open loop. There is no feedback on the human. Okay? So stability is not an issue. As far as the controller of the robot is stable, and this we take for granted, everything is going to be stable. You can do more interesting things. I don't know what that means, but probably this one is best. This is joint work with Arash and Nikos Tsagarakis, a work we did at IIT in Geneva. Here is again Arash, moving around and doing the classical peg in the hole task, which is a task where you need impedance control. The first time he uses high stiffness, he does insert the peg in the hole, but there are very high forces that are measured at the insertion. Then if you try to do with a low stiffness, we are not controlling the impedance here. We are setting the impedance stiff and then low. In the first case, you could do it. In the second case, you cannot do it because you are limiting, it's soft. And the third case is using impedance. So the impedance is measured in 3 directions. We have X, Y, and Z stiffness, and it's replicated on the arm. So the person, the student, is looking at the task, is not feeling anything, is just making his own reference in the hole, and is controlling the impedance in directions that would suit the task. And then, as you can see, when he stiffens up, it can extract. Before, let me show a little bit. This is nice, I think. Let me show it here. Yeah. So now what happens is that it goes there. Okay, so he goes there, then he finds the hole, and then he presses with the right impedance in the X and Y direction and in the Z direction to insert the hole. What you see then is that when it is inside, it tries to take the peg out with low impedance, it doesn't come. You see? Until It really, and unfortunately there is no sound, but there is a very nice pop sound when it gets out, you know, like this. Now, is this robust? I mean, this depends on calibration. If you do it the day after, is it going to work again? Or the month after? Or if you change the person? I didn't believe. So I needed to put my finger in it. And so we tried this. So these are, I dropped in the lab. I asked Arash, let's try. That was all the preparation. So he put EMGs on me, EMG electrodes on me, and we did the experiment. No preparation at all. I was using his calibration matrices of some time before. And if you look at my arm and you look at his arm, there's a huge difference. He plays tennis almost professionally. I do some biking. I mean, that's all I do. So my arm is half his size, and it still works. As you can see here. Okay, so far so good. I think we have covered the second part of the talk. If there are questions, you're welcome now, or maybe you can take them to later on. Yes. Yeah. Yeah. So here, here you have forces. Sorry. No, sorry. Here you have forces. Yeah. Yeah, this is the estimate of the T, of the map. Yeah. And this is the inverse, the pseudo-inverse we are using. And this is the projector in the null space. These are basically, EMG signals. I mean, these are the dimensions of EMG signals. Okay. I'm 50 minutes now. I have 2 more topics. I can try and go quickly through both of them, 3 of them actually. Or skip something. I think I will go very quickly through the first one. I think this is interesting, but maybe a little bit theoretical oriented. This is joint work with Giorgio Grioli, Alessandro Serio, Nikos Tsagarakis, Irene Sardellitti. And it's about measuring stiffness, something that we didn't do, we didn't hear so far in this school. Indeed, everybody here is concerned about changing stiffness and controlling stiffness. But we will make the point that for controlling stiffness, you might want to measure it to know what it is. And then we started thinking about that, and it came to us that we didn't really know what we were doing, so we started thinking a little bit more in detail. If you think of measuring something, it's no chance that physicists start with measuring. Whatever they talk about has to be measured. And this is no chance, I think. So let's think a minute about what impedance is. Simplest notion of mechanical impedance is a linear stiffness, right? Force is equal K times the deformation. Okay, so how do you generalize to nonlinear springs? Well, this is still easy. You have a nonlinear function of the displacement, and you take the partial derivative. Right? This is local. This is changing with the position, but anyway. This is what everybody would take. Then you do a step forward, and you generalize to dynamic systems. Then you basically now have a differential equation, still linear, a plus is missing here. And you have this system, and you typically do a transform. a Laplace transform, and in the space you call this operator an impedance, right? This is what we understand by impedance, probably most of us. So impedance is an operator that takes functions and sends these functions into functions. Right? Also, initial conditions are there, but if the system is stable, they will vanish. Okay, so impedance is an operator. How do you generalize this notion here in the nonlinear case? Of course, in the nonlinear case, you do not have Laplace. Okay? So you need to do something more complicated. Now, what you can assume you have, I think the most general view you can take is the following. You have a space of forces, positions, velocities, accelerations, and maybe some parameter that will tune the system. For instance, change the stiffness in the variable stiffness system. So in this whole space, you have a set of points that are feasible for that system. That means that you have a graph. And you can imagine doing an infinite number of experiments in this infinite dimensional space. And every time that you have a point that is an experiment, you have some position, velocity, acceleration, some setting, and some force. Paint a point in this space. And then you do everything, and you have a surface. You have a graph. You might hope to have an analytical description of this graph, which means some function of f, y dot, y double dot, and u equal to 0. If you do not have that, you forget about analytical description or definitions. If you do have that, you take any, this is a very simple example. You can think of a simple two-dimensional example. So you are somewhere here, for instance, or here, or here. Then at a regular point, d0, because of the Dini's theorem, which the rest of the world calls the implicit function theorem, in Italy, we call it Dini's theorem because it's due to an Italian, but it's a local viewpoint. So there exists an implicit function here. And of this implicit function, you can take a Fréchet differential, which basically is the differential, the derivative of a functional with respect to a function. So you do the derivative of these functional with respect to these functions, y dot, y double dot, and so on and so forth. Equivalently, you can rephrase this as saying that if you take the derivative of g with respect to d and you invert times the derivative of this graph times y, then this is k, yes. This what? I'm not positively sure about that, so I will hold it. Yeah, it sounds like, but I never thought about that. You can also take an admittance view and do the implicit function solution for y double dot instead of f, and then rewrite everything in terms of the dynamics. So this is what you call the admittance operator. This is a nonlinear system. Again, it's a differential equation, right? So if you have an antagonistic muscle, one of those models that we have seen before in this room, you can do everything here that we have seen, and you get the definition that match the normal understanding of this. Why am I saying this? Because to measure impedance, you need to know what you are doing. And measurements are the basis of science, and I have this co-citizens of mine, which say that one of his statements was, measure whatever is measurable, and make measurable whatever is not. For the rest, shut up. That was the meaning, you know. Feedback needs measuring. Measuring impedance is needed for control of VIA actuators, for instance. And impedance is a differential operator, not a physical quantity per se. If you think in strictly, I mean, narrow-minded idea of quantity, quantity is defined in metrology as scalars or vectors. And this is not. This is a differential operator. Just to point out a little of the difficulties. So anyway, we do measure impedance. How do we measure impedance? In mechanical engineering, in biomechanics, in robotics, impedance has been measured. Most often, we have repeated experiments with probing perturbations. So we have the arm somewhere, we probe with a force or with a displacement, and we measure the force or the displacement. They're mostly not applicable, those methods not applicable in real time, while we would like to have measurement while moving. And they're always linear, time invariant definitions of impedance. They're not really suited to our setup. So let's consider again the simple linear case. And now assume that you do not know M, B, and K. Can you, from measurement of positions and forces, knowing the force and measuring the position, can you infer information from M, B, and K? This is actually a nonlinear observability problem. If you are familiar with nonlinear observability, you can simply restate this problem in a nonlinear, in extended state space where Z is not just Y and Y dot, but also K, B, and M. Their derivatives will be 0, but they are states. So if you can observe the whole state from outputs, then it is possible to find all of that. And this is possible. It's easy to show that if you take the derivatives of the output, then it is observable. So you can imagine of doing filtering, identification of these parameters. You can do, for instance, an extended Kalman filter and estimate those parameters. But the same approach is no longer possible, at least not trivially, when you have nonlinear impedance. Because nonlinear impedance, you cannot simply build this model. If the impedance depends on the state, for instance, you have to know the model for the impedance before deriving this model. So you do not really have this solution unless you imagine some shape of this relation, and then you identify the parameters. So if you use an extended Kalman filter with a nonlinear impedance, it really doesn't work. So one thing to be noticed is that in our case, variable stiffness actuators, impedance is nonlinear. By definition, if you have agonist and antagonist, they have to be nonlinear in order to allow you to vary stiffness, right? So you cannot rely on linear stiffness. You have to be nonlinear. And it has to be time varying by definition of varying a variable stiffness actuator. So it is one problem that is harder than normal. Okay, so this was the most important part. The second part is, how do we do this? Then we need algorithms. EKF is not good enough. We have proposed it in 2010 in RSS, Robotics Science and System, an observer for this impedance, which basically only uses the measure of torque and position at the endpoint here, without knowing anything about the model of the stiffness. It's simply, very simply, using the model of the system, using M and B, so at this point, and differentiating this equation, you get the third derivative of the output. This is the derivative of the torque. You build an estimate based on your stiffness sigma, and you have an estimate sigma hat. This is how the torque would change with your best effort estimate. Then you compare your estimate with the true value, and you have an error in prediction. Then this error is the error in stiffness times the velocity. And at this point, you have an update law for changing the stiffness with time that will converge to the true stiffness within a small bounded set to the real stiffness value. And we have all kinds of results about convergence and time to converge and dimension of the set to which you are converging. This was in Zaragoza 1 year ago, roughly. What is interesting to say is that we are using, in this scheme, we are using velocities and derivatives of torques. Okay, notice this. I will come back to that. Well, there are some conditions. Of course, the faster the link moves, the better the estimate is, because it's exciting the dynamics. But if you have a parameter that changes the stiffness, for instance, co-contraction here, then this parameter that changes the stiffness is not observable from just the position and torque measurement of the link. So in this case, the beauty of this algorithm is that we are not using anything but the position and the theta and the torque tau at the link to infer the stiffness of the system. Right? Of course, if the co-contraction changes while the link is not moving, there is no way of measuring it from these outputs, right? So the whole idea is that while I move, I observe the torque and I observe the position. Right? And from this relation, without putting any perturbation in the system, this is a good point for this method, we are not perturbing the system, we are just observing motion. And observing motion, we can infer the impedance. Impedance can change while you move. But of course, if it changes while you are not moving, then you're lost, because you have nothing to observe. Simulations work well. What does the algorithm when the link is not moving? For instance, here, the link starts moving until here, and we track the stiffness correctly. Then from 10 to 20, the link is not moving, but the stiffness is changing. So the stiffness is changing along the green line. The algorithm simply stops because it has no information, so it stops at the last available measurement. And then when the link starts moving again at time 20, then the algorithm recovers very quickly the true value. Okay? So we find this very, very useful to measure stiffness in real time without perturbation, nonlinear time varying. If there are errors in mass and damping estimates, then you have more, the convergence is worse, but it still works, of course. We have bounds for that. Here are experimental results. We did a setup explicitly for having the capability of saying what the real impedance is. And these are experimental results. You see that there is noise. We are taking the derivative of noise, a dirty derivative. We are filtering them out, and it works. Here is the stiffness. The real stiffness is in green. The estimated stiffness is in gray before filtering, and you can see it tracks pretty well. You can filter this out if you want to. The relative error is about 20%. Notice that the accuracy by which we know the real impedance is the same order of magnitude, because estimating the impedance is difficult. Then there are a few more details. Can we do without M and B? Yes, if we measure here, not if we measure here. Sorry, here. But there are some evolutions, more recent. A parametric stiffness observer and a coupled impedance observers. Let me just go through quickly. If you do a parametric instead of non-parametric, then you can also avoid this problem of not observing, not having a true model when you have a static motion. And if you do, and here is a better reconstruction you can see here. And if you do, if you have both stiffness, damping, and mass that change, you can do a combination of this algorithm with other algorithms and estimate everything, stiffness, damping, and inertia in real time with no perturbations. And no extra sensors. Okay, so this is a summary I can skip. It's interesting to notice that the measurement, the derivative of torques can be easily replaced by torque error or even integrated torque error, the residuals, as it was done, for instance, by Alessandro De Luca very recently. Okay, so it's 1 hour and a half. Okay. So if people are still alive and well, I can go to the next topic, and I think I can do almost everything. I might, oh yeah, I have some water. Okay. So we move on to impedance and hence. What does impedance, variable impedance, has to do with hence? It will take a minute to understand, but it will be clear in a minute. So you now have to wipe out your mind a little bit, reset, and we start with a different thing. Something that has been brought forward yesterday in the discussion session. I don't remember who brought it up. Yeah, you did. And I said, yeah, we will see tomorrow. And here it comes. So now we go to a different problem, the problem of redundancy. How do our brain manage to control so many degrees of freedom, both actuation and sensing? The redundancy problem was called. You probably know more than I do, but there is extensive neuroscientific evidence for the existence of sensory motor synergies, whatever name you want to give to those, synergies, modes, primitives. I know at least 10 different names for this idea. That goes back to Babinski, the French researcher, and then great work done by Bernstein in Russia, and Emilio Bicchi and his group, and so on and so forth. There is some quantitative work on hand postural synergies that is dating back a decade or so, and which has been very useful for us to try to address the complexity problem of robot hands. So you might know of this kind of results. Here is a paper, for instance, by Marco Santello, who took 5 subjects asked to shape their hands in order to mime grasps for a large set of different objects. And then he took the measurement of the angles, and from these measurements he did the covariance matrix, and he did the principal component analysis. And then he saw that the first 2 principal components could explain up to 81% of the variance. Sorry for the displacement of these numbers. And the first 3 could account already for 90% of the variance of the data, meaning roughly that 3 degrees of freedom would be already enough to do 90% of the grasps, very roughly explanation. So these are, principal components are really eigenvectors of the covariance matrix, and they can be used to define a basis for the subspace of joint space, for coordinating the joints. It is, everybody's observation that hands do not move with independent joints, with completely independent joints. There are correlations in motions. And this tool that gave the quantitative data on what are the most often used correlations of motion. So if you look at the eigenvectors, you find that the first eigenvector is basically this motion here that we see on the left. Come on. Yeah. This is the classical grasping motion. Thumb opposing the middle finger. And then the second synergy spreads the hand a little bit. The third synergy does this opposition of this second and third to the fourth and fifth finger, and so on and so forth. So these are the groups of movements that are there. Now, whether this is mechanical to some extent or neural to some other extent, this is an open question. but it is observed there. So when you think of moving a hand with using only a limited number S of synergies, then you can think that all configuration of the hand move in a manifold that is S-dimensional. And you can call this sigma parameter the tuning parameter in this space, the coordinates in this space, so you see the hand moving. I never learned to use this thing. So the velocities will belong to the tangent space to this manifold, and then the fingers will move according to a Jacobian times the velocity of all joints, which then is the Jacobian times the synergy matrix times the velocity of the synergy coordinates. Does this make sense? This is very, very simple, right? Straightforward. So we are interested in grasping. Grasping means applying forces on an object to restrain its motion or to, exert forces on the external world. So, how have these synergies been used so far? They have been used for pre-grasping, mainly, to shape the hand to grasp different objects, using this as a database of pre-learned behaviors. So the question for us was, how do we really use this data for controlling forces and for avoiding slippage, for instance? So this is the first synergy, just to show what problems we are facing. This is the first synergy. This is the hand that closes with the first synergy. So assume you have a hand that only has one synergy, and assume that you want to grab this object. So what will happen? At some point here, you will get in contact with the object in this point and this point, maybe. So next, you close a little bit more, and something has to give inside, because the shape of synergy does not necessarily fit any particular object. Okay? So what you do with this at this point? There are a few groups that have used synergies to design hands or algorithms. This is a group at MIT who designed a very nice hand that has all wires arranged in ways that the hand with two motors moves according to the first two synergies. So what they do when they get in contact with the object, the hand closes, get in contact with the object, the hand stops. Another possible solution is here. This is Peter Allen and Matej Ciocarli. They do the same. They move the hand until they reach the object. So assume that this is the first contact. At that point, they stop these fingers and they continue with the others. And then the second and third and so on and so forth, until they reach the whole contacts. Now, of course, this is okay if you want to get a grab. But this is not going to respect the synergies because this is changing the whole geometry depending on the object, right? Also, both were not interested in controlling the forces at contact. We are interested in that specific problem. So we are interested in grasping. That means how forces are applied and controlled. A purely geometric synergy model cannot account for grasping force generation. And what relation is there between grasping forces, grasping postures, and synergies? That's the question. So if you do the analysis of grasping, let's go through the basics of grasping analysis. I think it's very simple, but I hope you have had some exposure before. So let's W be the external wrench that acts on the object. And let P be the contact forces at the fingertips. Then you have a linear map, which is basically a force balance map, which is called the grasp matrix. It's a fat matrix, typically. So this in equilibrium, the contact forces at the fingers balance the external wrench through this grasp matrix. Then you have to take into account friction constraints. At every contact force P has to be within the friction cone to avoid slippage of the object. And you have constraints written in terms of the components of the contact forces. Then the question typically is, given some external force, which contact force should I have on the fingers to avoid slippage and balance that wrench? Yeah. So solution typically is some right inverse of G, that means some particular solutions, plus some homogeneous solutions. Whatever is in the null space of G here does not contribute to the balance, but can be very useful for the constraint. So you have an object, you can, for instance, squeeze it more. It does not change the external wrench, the external force, but it does change the properties of slippage. For instance, if you hold it this way, you will use a different grasping force than if you hold it this way. You will squeeze a little bit more if the weight is taking the object out of your hand. Yeah? So how do you do that? You use this null space term here. These are called internal forces. So A is a basis of the subspace of internal squeezing forces. By changing this parameter x, you are changing the squeezing forces, and therefore, if for every external wrench you can find internal forces such that you respect all friction constraints, then you call this grasp force closure. You might have heard about this name, force closure. I think this only holds for fingertip grasping with a large number of synergies. It's not in generally true. This is not the right problem. This is the classical but wrong problem. Indeed, it is not true that you can apply arbitrary forces at the fingertips because simply the torques that you have at the joints are tau, and this is the hand Jacobian, and these are the torques that you have at the fingertips. So if this matrix is not invertible, you cannot simply find a solution for every p given tau. This is even more evident if you have synergies, because then you only have degrees of freedom along the synergies. So if you are using one or two synergies, you have one or two torques, independent combination of torques. And you might have many contact point coordinates here, 15, 20. So it's not possible to invert this. So you cannot apply arbitrary contact forces P. So let me do this. This is a very simple example. Take this grasp here. You have 5 contact points. You have 15 components of frictional contact forces. At every contact point, you have 3 components of force. You have 10 joints. Therefore, you have already in this grasp, you have less joints than components of contact force. So you cannot apply an arbitrary contact force. Therefore, you cannot apply an arbitrary combination of internal forces to go into that null space. The situation is even worse if you use synergies. Assume that you are using one synergy, for instance. That basically means you are using 1 degree of freedom. You are connecting contact forces and using 1 degree of freedom that combines all of them. Therefore, in this case, you have only 1 to control 15, which is impossible. So how do synergies come together with forces? Well, this is a statically indeterminate problem. There is no way to determine P from given W and torques. There's little you can do about that. You have to introduce congruence and constitutive equations. That means compliance. So you have to include compliance, how the position of the fingers and the position of the object determine the relative position of fingers and object, determine the contact forces through the hand compliance. Once you've done that, you have to consider what is the hand compliance. Hand compliance is made of 2 parts. Hand compliance is due in part to the fact the object is compliant and the finger pads are compliant, where you have contact, but also because of the fact that the fingers are not really rigid. So how do fingers work? Fingers work like any other joint. They have mechanical compliance, which is negligible probably. And then they have compliance with respect to the reference position. Typically, you want the finger to be at some position, then if you press it, it will deform, right? And if you take this joint compliance, which is the compliance between the reference and the real position, this can be changed, of course. It can be changed by setting the reflex level. You can make it stiffer or not. It depends on how you set. So it's basically this part here that you can control. This is the stiffness at the joint level, which is brought to the overall grasp stiffness K through this easy formula here. Okay. So you do the analytics of this, and there is a little theorem. The set of contact forces which can be actively controlled is a linear subspace of the null space of G, which is given by this formula here. This is the null space of G. This is K. This is Jacobian, the synergies, and the change in synergy references. I think this is interesting. This is how synergies get into the play. And these are the contact forces that you can really control. So when you want to optimize grasping forces, you can only rely on these and not on everything which is in the null space. As you can see, you are reducing the dimension of the forces through this operator here. So this, let us step back a little bit and look at it from the higher level. Yeah. The posterior kinetic synergy model only rules an internal reference representation of the hand configuration. The higher level control of the hand commands this internal representation within the synergy manifold. The actuator system of the hand is controlled towards this reference hand set point. The hand fingers and palm interact with manipulated objects and environment through contact. And the physical hand reaches an equilibrium under the effect of attraction towards the synergy-driven reference hand, repulsion by contact forces, and stiffness of actuators, tendons, and deformable bodies. So in some sense, I think, after hearing so many talks here today, I think you can take this, probably you would call it lambda. If you know what I mean. Lambda is the name for the lambda model, Feldman model. This is really consistent with that. Then how you design trajectories for lambda, this is probably an internal model problem. But this is only, an afterthought. And so this is the solution you have. These are animations. This is the hand grasping the object. And the reference hand, the equilibrium hand, going inside the object. The real hand staying outside the object. And I have 1:25. So in my clock, I have 5 minutes. Okay, yeah, I guess don't vote. I know the result. Okay, so let me skip all of this now. But there are some interesting results showing that indeed in the force domain, the first three synergies that are important for positions are also dominating in the force domain, saying that this model makes sense, makes a lot of sense. I just want to conclude a few notes about the actuators and the physical actuators we are building. So we started this project in 2000. Then through years, we have come to more and more sophisticated devices. And we have today an interesting device, which is the Qbot. It's a very small variable stiffness actuators. The idea here is that we would like to have something that people can use freely. Devices such as DLR are very beautiful. But unfortunately, they're very costly also. We would like to have VSA diffused on a large scale, and people who are not interested in doing their own mechanics could simply use them and explore different applications, different possible exploitations. So here are the data sheets for this cube that we have developed. The cube, I have no time for the details. The data sheets are available on the website. It's a modular device that can be combined. Let me just skip all of this. It's a modular device that can be combined through fixtures, easy fixtures. It's a variable output shaft stiffness, embedded position, and stiffness regulation. There is a bus communication interface, standard bus communication interface. You can simply plug them in and build devices. So for instance, you can build animals or arms or legs out of this. It has been licensed to a small company that will make this available at a very low price. And here is the first little humanoid that you can build out of these things. So this humanoid would cost substantially less than $10,000. Okay. You can do little things like throwing, hammering, drumming. It's very safe. You can interact with that. It's also very robust.